by now, hopefully you have some idea of what an inertial frame of reference is. And in the rest of this lesson, we are going to be focusing on only inertial frames of reference. Later in the course, we'll be talking about non-inertial frames of reference, but for the relative motion here, we'll be focusing on inertial frames of reference. So let's do some examples. If you're riding in a train traveling 10 meters per second north and you roll a ball down the aisle in the train towards the front of the train at 2 meters per second. So you're sitting on a train, you roll a ball forwards, and the train is traveling north. So just sort of off to the side, just going to do a little sketch here. Let's make that right. So here's the train traveling north at 10 meters per second. And then here's you on the train rolling the ball at 2 meters per second. Now, there's different motions happening here, and they're all sort of happening at the same time. And that's sort of what we're going to get at in this lesson, how to sort of sift through the confusion and sort of come up with a notation that's going to make it really easy for us to answer questions like this. So the first question asks is, what's the velocity of the ball from your frame of reference sitting on the train? So if we're sitting on the train, even though the train's moving at 10 meters per second, that doesn't really matter to us sitting on the train. We can be moving at 100 meters per second, 1,000 meters per second. It doesn't actually impact that ball rolling forwards. In fact, we couldn't even tell. If the train was completely sealed up with no windows, we couldn't even tell we were moving at a constant velocity, assuming there's no bumps in the track or anything like that. If the track was completely smooth and we were inside, we wouldn't be able to tell, because moving at a constant velocity, we know the net force is 0. So we wouldn't feel anything. So if we just are sitting on the train and roll the ball forwards, assuming we know the train is traveling north, we could say the velocity of the ball from our perspective is moving at 2 meters per second north, right? Now, some notation that we could use for that. So we're looking for the velocity of the ball, but the frame of reference we're looking at here is from the train's point of view. So we use subscripts. The first subscript represents the object moving. The second subscript represents the frame of reference. So we would say that that is 2 meters per second north. Now again, what that BT means is it means of the ball, so velocity of the ball from the perspective, or in the frame of the reference, let me put that, in the reference frame of the train. Okay? So, if the reference frame is the train, the ball is moving at 2 meters per second north. Now, what is the velocity of the ball from the frame of reference of somebody standing on the ground watching the train go by? So if you're standing out here watching the train go by, what's the velocity of the ball going to be? Now, it's a pretty simple question, right? Like, we know the train is moving at 10 meters per second in this direction, and the ball is moving at 2 meters per second on the train. So, I mean, it's pretty clearly that the ball should be moving from your perspective at 12 meters per second, right? And that actually is the answer. It's just 12 meters per second north. Nothing special about that. So let's assume that this railway car, let's pretend it has like one-way glass. So you can see into the railway car, but the person inside can't see out. So you can see the ball moving at 12 meters per second if you're standing beside it. Now, what we're trying to find here, so mathematically, how does this look? So if we're trying to find the ball with reference, the reference frame being the Earth, E is what we commonly use for the Earth, or like a stationary object on the Earth as the reference frame. So we would say the velocity of the ball with reference to the Earth, and we know the answer is 12, but in order to mathematically show that, we can use some subscripts. So what we do know in the question is we know that this 2 meters per second, we know that's the velocity of the ball with reference to the train, right? And we also know that this 10 meters per second is the velocity of the train with reference to the Earth, right? So we would say that this is V, the train, with the reference frame of the Earth. So we have these two separate velocities, and the way we can think about it is you need to go from the reference, from the ball to the Earth. how do you go from the ball's reference frame to the Earth's reference frame? So we start with the ball to the train, and then we go to the Earth because we know that the speed of the train with reference to the Earth. So it may sound like I'm making this more complicated than it needs to be, but trust me, it's going to make it easier for questions later that are more complicated. So we have the velocity of the ball with reference to the train, and we can add to that the velocity of the train with reference to the Earth. Okay, so do you see that? To go from the ball to the Earth, we had to go from the ball to the train, and then from the train to the Earth. So think of it sort of like a chain of things that we need to add together. And if we do this, we see that this is 2 meters per second, the ball with reference to the train, 2 meters per second north. And then we have the train with the reference frame of the Earth is 10 meters per second north. So the answer is just 12 meters per second north. Okay? So it seems like more work than it needs to be, but trust me, when the questions get more complicated, this will make sense. Next, what is the velocity of the ball from the frame of reference from a person in a train moving at 15 meters per second south? So now, let's get rid of this person here, right? And let's say there's another train that's moving south at 15 meters per second. And let's say you're now standing on this train and you're watching this other train goes by. Let's assume that you can see out of the train. You see the other train go by and you look into that train and you see the ball moving in this direction. From your reference point here, how fast is that ball moving? We're going to need to take this into account somehow because, compared to you, it's sort of as if you were standing still. Pretend you were standing still in this railway car, like you couldn't see the Earth around you moving. You could just see into this other railway car. How fast would it be going by you, right? And probably because, you're moving fast in the southward direction, it's going to be a pretty fast speed, right? So let's think about this. What are we given in this? What is this 15 meters per second? How can we say that in terms of like our notation? Well, this is a speed of, we can call it train 2 with respect to Earth, right? If we know that the train is moving with respect to Earth. So what we want is, the speed of the ball with the reference frame being train 2, right? So we need to somehow get from the ball to train 2, right? So let's think about what we have. If we think about like our chain of things that we have the speed of the ball with reference to the train 1, right? So we can go from that to that. Then from train 1, we know the speed of train 1 with reference to the Earth. And we also know the speed of train 2 with reference to the Earth. So we need to go from Earth's reference frame to the train 2 reference frame, right? So again, we need to start at the ball's reference frame, turn that into the train's reference frame, turn that into the Earth's reference frame, turn that back into train 2's reference frame to get from there to there, right? So in terms, mathematically, we're going to start with our ball with respect to the train 1. Then we're going to add to that the speed of train 1 with respect to Earth, right? That's this part here. Then we need to go from the Earth's reference frame to train 2. Now, we're not actually given the reference frame of Earth with respect to train 2, right? We're given train 2 speed with reference to Earth. And this is a weird thing because we don't usually think about Earth moving, but pretend you're on the train, and to you it doesn't feel like the train's moving because you're just moving at a constant speed. What speed would the Earth be moving past you? Well, if you're on the train is moving south. Another way of thinking about that is you're stationary on the train and the Earth is moving north at 15 meters per second, right? So the way we can do is we just reverse it. To find the speed or the velocity of Earth from the perspective of train 2, it's going to be 15 meters per second north, if this is 15 meters per second south. Because if you were still on the train, from your perspective, it could look like the Earth is moving north past you, right? So to finish this equation here, our speed of Earth with reference to train 2 is that going to be that 15 meters per second north. Then we can add all these things up. So we know the ball with respect to the train, that's 2 meters per second north, right? We know the train with respect to the Earth, right? Train 1 with respect to Earth is 10 meters per second north. And we know the velocity of the Earth with respect to train 2 is 15 meters per second north. If we add all those things up, what do we get? 27. We get 27 meters per second north. Okay? So it might sound confusing, especially the part where it's like the reference speed of Earth with respect to the train. But this way, this process of doing it ensures that you're going to get to the right answer just using a little bit of, algebra. In general, we can describe the velocities with the following notation. So if we're trying to get through things like A to D, right? So the velocity of something of object A with respect to D. So let's say there's 4 different speeds involved. We would do the velocity of A with respect to B plus B, the velocity of B with respect to C, plus the velocity of C with respect to D. You just follow along with the chain. Start with A, go to B, go to C, and then you end up at D. Okay? So that was a one-dimensional example. Let's look at a two-dimensional example now. If you go swimming in a river that flows at a speed, or it should say a velocity, of 5 meters per second south, so if this is our river, clearly the river has to go north-south if the flow of the river is south. So this is 5 meters per second south, right? Now, what could we call that speed? What is that speed? What's the reference frame of that speed? Well, I mean, it doesn't really say, but we can assume that that's the speed compared to like the ground around the river, right? The Earth. So we would say that this is the speed or the velocity of the river with respect to Earth's reference frame, right? So we would do RE like that. Okay, your average swimming speed is 3 meters per second. Okay, cool. We should also, by the way, we should have done this in the previous question with our diagram, just draw a quick compass, north, south, west, east. So if you were to swim straight downstream, what is your velocity relative to a person standing on the shore, right? So relative to a person standing on the shore is just like saying a person on Earth, right? So we already know the river with respect to Earth is 5 meters per second, but we also know our swimming speed is 3 meters per second. So the swimming speed is going to be also south in a direction of 3 meters per second. Now, is that swimming speed, what is that in reference to? Well, when you're in a medium, like you're in water, sort of the reference speed that you're going to have is going to be based on that material you're in, right? So if you're moving with a river, the river is carrying you with it, right? So that 3 meters per second is going to be in terms of a reference frame of the moving water or the river. So we could say that this is a speed of us. What do we want to call us? I'm going to put S for swimmer. So VS with respect to the river, right? So if we want in this question to find the speed of us, or the swimmer, with respect to Earth, right, a person standing on the ground, we would need the speed of the swimmer with respect, well, we don't know the swimmer with respect to Earth yet, but we can see it's going to be the swimmer with respect to the river plus the speed of the river with respect to Earth, because those are both things we have. So essentially we're just adding that up, 5 meters per second south plus 3 meters per second south, which gives us 7 meters per second south. Okay, if we swim straight upstream, so we're actually just changing this around. Oops, erase that. Changing this around to an arrow going upstream, right? So it's the same thing, right? It's just we've changed our direction. So our velocity of our swimmer with respect to Earth is going to be our velocity with our swimmer with respect to the river, plus our velocity with our river with respect to Earth. So in this case, the swimmer with respect to river, well, the river is moving south. From the point of view of the river, you're trying to swim 3 meters per second north. So it's 3 meters per second north plus 5 meters per second south, right? So the thing to keep in mind here is you can't add two things if they're in different directions, so we need to turn them into the same direction. The easier way to do it is just define north as positive, right? So if we define north as positive, then it's going to be 3 minus 5, which ends up being negative 2 meters per second in the positive direction in north, or even better, 2 meters per second south. So let's think about what that means. Even if you swim upstream, the river is pulling you basically south at a faster speed than you can swim. So you are still moving south at 2 meters per second, right? Okay, if you point yourself directly across the river and swim from the west shore, what is your velocity relative to a person standing on the shore? So again, let's change this diagram. Now, we're going to swim from the west shore. So the west shore is over here, so we're going to swim, oops, let's do that in red. We're going to swim directly across, like that. Well, that's where we're going to point ourselves and start swimming, right? What's going to happen? Are we going to actually end up going directly across the river? Well, you should see, if I move, let me move this actually. Oops. Let me move this 3 meters per second. If we start trying to swim directly across the river is going to pull us in a south direction, right, while we're swimming. So we're going to end up going like in a direction something like this, right? Does that make sense? Because, our velocity is going to be the combination of these two velocities, right? And we know, again, that this one is 3 meters per second. And we'll call that VSR. So now, it's the same thing, right? We're still doing the velocity of the swimmer with reference to the Earth, but this time, well, it's going to be the same thing. V, the velocity of the swimmer with respect to the river, plus the river with respect to Earth, but this time they are not in the same direction. We're adding a swimmer with respect to the river, which is 3 meters per second east, and we're adding to that the 5 meters per second south. So we can't just add 3 and 5 to get 8 because they're in different directions. And we should see, to add these, we need to add the vectors, right? So very quickly, we have a 3 meters per second going in this direction. We have a 5 meters per second going in this direction. The result of swimming there is going to be the sum of those two, right? So the actual velocity, the velocity of the swimmer with respect to Earth, swimmer with respect to Earth, is going to be the sum of the vector sum of those two, right? So we can use a little bit of trigonometry to find out the length of VSE, right? Just using the Pythagorean theorem. So it'll be 3 squared plus 5 squared, and then take the square root of that, which would be 5.83. So basically the speed that we're going to be traveling at is 5.83 meters per second. That's rounded to 3 significant. So a little more proper, let's just make that 6 meters per second for the one significant figure in the question. And then we also need the direction for a velocity, right? We want to know this angle. And of course, we can just use arctan or inverse tan of 5/3. I'm not showing all the work here because I know you should be able to do that part yourself. But 59 degrees. So this theta is 59 degrees. So that's also going to be east 59 degrees south. So there we go. That's our velocity of the swimmer with respect to the Earth, or with the Earth as the reference point. If you swim directly across the river from the west shore, what is your velocity relative to a log floating down the river with the current? So a log floating down the river is just going to have the speed of the current, right? It's going to look like that, right? So what we're trying to do is we're trying to find the velocity of the swimmer with respect to the river, right? We're trying to find the velocity of the swimmer with respect to the river because the log is just floating along with the current of the river. The weird thing is this question, we already know what the velocity of the swimmer, or the speed of the swimmer with respect to the river is. We know it's 3 meters per second. But the question is now, there's a direction in play that's not along with the current, it's east across the river. So it's 3 meters per second east. Because think about it, that log that's floating down, so if there's a log here, just can't really see that. If there's a log here floating down the river at this speed, to the log, it's going to look like, because everything, sort of the swimmer is being dragged down the river at the same speed that the log is dragging down the river. So to the log, it just looks like the swimmer is swimming directly across the river, right? Even though they're both moving down on an angle. So this answer makes sense. Now here comes the thinking question. What direction should you swim at to swim directly across the river? So I'm just going to draw another quick sketch here. We know if we were to try to swim directly across the river, we'd end up downstream, right? If we started here and we swam directly across the river, we'd end up downstream. But is there a speed that we can, or is there a direction we can angle ourselves so that when we basically start swimming across the river, we're going to end up going directly across the river? So basically, we want a speed that we can cancel out this 5 meters per second, right? So what we have to do is we have to sort of pick an angle, a theta, to make this true. Now, this is a bit of a trick question. How fast is the river moving? 5 meters per second. How fast is the fastest speed that you can travel at? Well, we assume it's an average speed of 3 meters per second. Is it actually possible for you to swim directly across the river? Well, think about it. If you swim directly up the river, you're still moving down the river. So it's actually not possible to swim directly across the river because you're always going to end up getting pulled downstream because the current is too fast, right? It's not possible. But if it was possible, if say we swam faster, you could analyze this in a little bit of a different way, right? What you could do is look at it in terms of sort of almost like a free body diagram, but for vectors, for velocity vectors, right? We would want some theta from the horizontal with this 5 meters per second. We would want some way to cancel out this 5 meters per second, right? So in other words, we would want a component of this vector here, of the speed vector, to cancel out with it, right? We would want this vector to have an upwards component of 5 meters per second, which we know is impossible in this case because the speed is 3 meters per second. You can't have a component that's bigger than the actual vector. So if the question was a little bit different, and you might get a question like this in your homework about how to swim directly across the river, you can think about that. How can we cancel out this with this? What angle would we need to swim at if we know this length to cancel it out? All right? So there you go.